The last application that we're going to see where LSTMs will actually be used is the neural machine translation. In this kind of application, I mean, you probably have used machine translation extensively. For example, today we have real-time or almost real-time kind of neural machine translation in every smartphone, where there is an application where you record your voice in English and you can translate it to any other language and so on. But in general, the neural machine translation is one of the many applications of what is more generally called sequence-to-sequence models. So in the sequence-to-sequence models, we are going to be dealing with here is we're going to start with the LSTM kind of treatment of the topic, and then we are going to be introducing sequence-to-sequence with attention, and this is actually going to be giving us quite a lot of visibility into what we are calling transformer architectures, because transformers, as we said, started from sort of sequence-to-sequence models, the so-called encoder-decoder models, and then evolved those models to create, you know, the revolution we are seeing today in the field of natural language processing. So I will be motivating the discussion from the translation kind of perspective, but the sequence-to-sequence models are a bit more generic. In fact, you can have sort of any sort of the applications quoted over here. Let's say the summarization, where we have, let's say, a body of text that we would like to create a concise summary of it. We can actually have any sort of a sequence-to-sequence model to take some kind of code as input. I take natural language as input and converting into code. That's another sequence-to-sequence task, and so on. All right, so in this respect, what we are going to be doing is we are going to start with the neural machine translation with a sentence which is in the in Greek. So let me write this sentence in Greek. Okay, so this sentence, we will be sort of symbolizing this sentence with X. So we have here, let's assume the simple case where we have a word level tokenization to avoid any complications. So X1, X2, X3. And translation, which is I love you. So that's basically, and here we are actually seeing also the simplest case where we have exactly the same tokens at the input and the output. Although obviously this is not going to be the case in general. So the sequence-to-sequence model consists of the so-called encoder-decoder architectures. In other words, we are going to be creating a probabilistic machine again that will consist of these two parts: an encoding part, where we are going to take the input sequence X1, X2, and X3 and create a representation of that sequence, and a decoder part that will start from that representation that the encoder built, and we are going to translate it to create, if you like, the individual, the translated tokens, which in this case is X primes. Okay, so in terms of architecture, it will look like this. We'll start from some initial hidden state, let's say all zeros, H0. Again, I'm not going to be drawing the full LSTM cell here, but in practice, this is an LSTM cell. And we are going to also introduce some kind of enhancement to the simple LSTM cell, not the cell itself, but some enhancement to the overall kind of architecture we have seen earlier in a moment. So here we have the sort of some input X. We'll see exactly with what order these X's arrive. So that's the third token. And this is what the representation phi, we'll call this representation phi, what the encoder is generating. And here's the decoder So the decoder is starts from a token which we'll call a start of sentence. And during the training, we are using the ground truth, and we have here the prediction is the prediction of the translated token. In this case is I, in this case is, in this instance is love, and this is you. And when U comes in, what we are predicting is another token which stands for end of sentence token, or EOS. Okay, so effectively the decoder is triggered by the arrival of the start of sentence token. So there is certain things that need to happen during the tokenization step in order for us to insert these actually tokens and prepare our data set appropriately. And it ends with the end of sentence as the prediction. That's the whole process. This phi is going to be called the thought vector. Thought vector. Okay, and one trick that we are actually doing in sequence-to-sequence modeling is the fact that we are feeding the input sentence in kind of a reverse order. And in many languages, we are doing so because in many languages, the very first word that is being translated is very much the word that it is the very first token of the source language. So the source and the target are kind of aligned in many languages, not all languages, but in many languages that's the case. And what we want to achieve here is that we would like to bootstrap the decoding kind of process. In other words, this X1 to be a recent addition into the hidden state and of that at this point in time of the RNN, in order for it to get a good start from the very first token, which is in the target language. Okay, so in terms of so this is one point that I want to explicitly do. So the other thing is, let me write it down. We typically feed the tokens into the decoder with the reverse order. Another thing we actually do is we are implementing what is actually called a bidirectional RNN. So let me write down bidirectional bidirectional RNNs are used, and the way to actually understand that is the following. And let me give you an example to so let's assume that we have, let's say, two sentences. The troops were loyal to George Washington. And the second sentence is George Washington is a parking lot, is closed to traffic today. So in many instances, we have the following kind of problem. So the meaning of, let's say, a term, let's say as this sequence of tokens that corresponds to a name, like George Washington, can be, sometimes it's a function of what follows or what it precedes it. So, in this case, what we're trying to do with the bidirectional RNNs, in order for us to achieve that thought vector to contain both types of representations, we have effectively forming two hidden states. One by looking at the tokens in this order, and the other by looking at the tokens in that other order, the forward and the reverse. So I'll be calling the phi f the first one and the phi r the second one. Okay, so we have two vectors and we are concatenating them together. Needless to say that the phi f is the last hidden state. Is the last hidden state of this encoder RNN. So this is my encoder RNN. And the moment we have this representation built, we are effectively feeding into the decoder. That's my decoder. Okay, so that's basically the second thing I wanted to mention. So the third thing is we wanted to distinguish between two things: what we do during training, during the training protocol, if you like, and what we do for inference. So we use the term teacher forcing to describe the process that during training we feed the ground truth via the decoder input, but during inference, and this is actually what we are going to be doing, is we are going to feed, and this is how I show it with this kind of dotted line, we are feeding the previously predicted token as input to the decoder. So during inference, feed the previous predicted token as input to the decoder. And obviously we have to be dealing with all this kind of complications, and we have a kind of an extensive notebook on implementation of this sequence to sequence neural machine translation with LSTMs. Evidently in this notebook you will also come across the fact that the cardinality of the source is vocabulary is not obviously the same as the cardinality of the target. Okay, and this is basically our sort of normal situation we're going to see exactly how we're going to address. Okay, so let's, now that we understood the block diagram, we have, if you like, the block diagram in front of us. Let's see a little bit more mathematically what it is really this P model, what is the the probabilistic machine that we have built. So the encoding process is effectively solves calculates a thought vector phi, and it effectively models via the encoder RNN. So I'll mention this in the literature. This come across as Q, the function of the encoding RNN. Evidently, there is a P model behind it. There's a probability distribution behind it, but here we write, if you like, the sort of simplifying this kind of notation, and we have a function that effectively takes as input this hidden state h1, h2, dot, 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 htx. So we met this capital T notation in the when we looked at the language kind of models, and over here we can tx is the length of the source sentence. All right, so that's basically what the phi vector is calculated, and we've seen that how it is also concatenated with forward and reverse passes, and the decoder, and that's basically where this name came from. The so-called conditional language model is from the decoder perspective. So the y hat which is being calculated, which is the sequence of words, but y hat is being written here as as a general sequence of predictions. So we have here an argmax over all sequences y of p of y given phi comma theta. So this is the P model. And in fact, I think that just because the literature uses Q, we can actually, for notational simplicity, we can also call this the P model. For this P model is for the encoder. And this is the decoder P model. Okay, so these are architecturally identical in a sense that both are based on the LSTM kind of neural technology. All right, so let's write this down a bit more explicitly. So I do not want necessarily to confuse this y under bar with a vector. So maybe we can just call it like this. This kind of a sequence of output tokens of target tokens, and the same thing can go here. So we have here an argmax over y of a P model of y1, y2, yty given phi comma theta, where ty now in this case is the length of the target sentence. All right, so what we actually can see here is that we can actually make a similar simplification to the calculating of this this model that we have done earlier when we were discussing language models, or actually when we're discussing Word2Vec in that kind of video. So we can actually write it as argmax over y, in this case now, of P model of yty given y1, y2, yt, y minus 1, comma, phi, comma, theta. In fact, we don't need to make, in this case, any simplifying assumption. This is just a factorization from first principles of that kind of a joint probability distribution. We can always factorize a joint probability distribution as a product of the individual conditionals. For example, to open a parenthesis here, you can actually factorize P of x1, let's say y1 comma y2, as P of Y2 given Y1 times P of Y1. And this was the case, this was met in another video as kind of the product rule, so we're not really breaking any new ground here. We're just rewriting this as a product of the individual probabilities. So this is now P model times ... P model. Finally, we'll arrive at Y2 given Y1, comma phi, comma theta, times P model of Y1, comma phi, comma theta. Okay, so this can be simplified as argmax, in terms of notation at least, over Y, the product from t is equal to 1 to t of y, p of yt given y1, yt minus 1, comma phi, comma theta. And this is the reason why the Newton translation is actually called a conditional language model, because we are actually conditioning on the thought vector. Okay, so now that we actually have seen in terms of equations what is being done, if you like, in this kind of block diagram, with this kind of block diagram, let's look at an implementation and see how this evidently the decoder is going to involve some form of a loss. So that in the decoding part we have to attach some form of a loss. Now we'll see exactly what are these loss functions, but I think it's better to see that in implementation rather than continue to write it in a math notation here. Before going into the notebook, I think it's worthwhile kind of highlighting a couple of things here. We need to explain a couple of things because it's not entirely straightforward exactly how we will be implementing this kind of argmax operator, which we have seen quoted in the equations of the decoder P model. So the first thing that we wanted to highlight is the fact that we are going to have deep RNN architectures here, so deep LSTM architecture. So we have a video on RNNs and LSTMs, so for those who want to review that topic, then we explained there what is a deep architecture is. So we are going to be gradually building up hidden state representations over multiple layers. That's one thing. The second is that, which is a bit more nuanced, is actually going to be described using this picture that we have offered earlier. So the decoding during this kind of a decoding process, so we are going to pick up losses at every part of the translation process. For every stage of the translation process, there's going to be some loss function. Obviously, it's going to be cross entropy loss because we're making a prediction over a discrete set of classes, which is, of course, the vocabulary size, the target vocabulary size. Okay, so the V target over here. So we are, for every loss that we are calculating, we are going to be doing backpropagation through time. And in this backpropagation through time, we are going to pass the gradient over into the encoder as well. So the trainable parameters of the encoder and by extension the produced thought vector is a function of how the decoder is doing. In other words, we don't have decoupling here. We have, if you like, a joint parameter optimization as you might have expected in this kind of architecture, but I thought to mention it explicitly. So that's, so let me write it down, joint parameter optimization of encoder and decoder trainable parameters. Okay, so that's the other thing, of course, I wanted to mention is that, which is a bit more nuanced, is the following. At every step of the way, what we do, we are actually doing a kind of a greedy decoding process. So remember that this is an unrolled diagram. So physically we have this step at this point in time. So we are selecting the next token, the translated token, based on the fact that we are taking, if you like, a softmax over all the probabilities, over the posterior probability distribution we have at the output. So that softmax, which is a software version of argmax, is the reason why I actually call that kind of a greedy process. So we do not consider for the translation of this token any other token which may come next to it, or for the translation of this token any other token that it was produced before that. So we have some form of kind of a memoryless greedy process going on in the decoder process. So that is has been shown it is not really the best thing we can do. In fact, if you take a note on, and this reason I actually wrote down the sort of calculations here in a bit more conditional probability distributions here. So what we actually can see is that we need to be taking, an argmax over the sequences in order for us to solve optimally the problem. So what we need to do is we need to have an add-on algorithm that it will be correcting some of the predictions that we actually are making. And this algorithm is actually called beam search. And correcting is actually a strong term, where basically is path selection at the end. And now we will need to discuss this algorithm because this is basically what is extensively used in practice. So let's now spend some time explaining the beam search, and then we can go to the notebook. This beam search has its roots on a very famous algorithm called maximum likelihood sequence estimator, also known as the Viterbi algorithm, from inventor Viterbi. And in fact, this algorithm is being implemented in many places, including all your smartphones, to receive radio signals. Okay, so let's start with an example. In this example, we have the following kind of a decoding process. So as we discussed, we start with a start of sentence token, and we probability at the output of the softmax in the very first decoding step, we produce the token, we predict the token V. Okay, because it's a probability 1, we have no other tokens. All of the other tokens are 0 because the output is a posterior probability distribution. Then we go to the second decoding step, and again with probability 1, let's say we decode we predict the word ship. All right, and then we have here in the next decoding step, however, we have a sort of a token that is predicted with probability 0.6 has, and with probability 0.4, let's say, sailed. And over here after has, we're going to the kind of a final step, which is the word docked and the word sunk. So this was predicted with 0.55, and as you might expect, 1 minus 0.55 is 0.45 for the word sunk. And of course, there is this end of sentence kind of token after that. Okay, we are not going to draw that. Okay, so we have sailed over here. After sailed in this branch, we were predicting some, home, and away. Okay. Okay, so the home here was 0.9 and the away 0.1. So, obviously during the, the beam search algorithm is actually happens in inference time, where we have, if you like, a model, we are forming, because obviously during training we have the ground truth, so we don't have anything to sort of worry us at this point in time. But during inference, what is happening is the following. So as we discussed, we adopted a kind of a greedy approach. So this one would actually have been selected greedily. So out of the two, hasks will have been produced at the output. And over here, docked will have been produced at the output in the greedy approach. Okay, because between the two, so the path that will have been produced at the output is this one. So let me write this down. So in the greedy decoding, so greedy decoding does not maximize the likelihood Actually, I'm writing the wrong conclusion. We'll come to this conclusion a bit later. But what I wanted to write here is that, according to the greedy approach of selecting the token with the maximum posterior probability at any instant in time the decoder produces the SHIP has docked. Okay, so, and this is actually going to be not necessarily the decoding that would have actually resulted how we selected what the decoder, the actual equation is telling us to do. Because the actual equation is telling us to select the most likely sequence over, to take the Armax over all the sequences. So what we actually need to do here is calculate the probability or the likelihood of every sequence. So if we are to do that, then this probability will end up being 0.55 times 0.6. So this will actually be 0.33. So let me write it down as the, let me write it down over here with maybe a red thing. This is 0.33. And out of the many others, we actually can see here that this probability will actually be 0.36. But we never produced this. So what we need to do now is we need to come up with an algorithm that will actually allow us to select this path. In fact, this is the most likely path that we have to select. Okay, so this is achieved with the beam search. So with beam search, so let me write down the fact first that I was writing earlier. So greedy decoding does not maximize the likelihood of the sequence of translated tokens. And the second is that the solution, which is beam search, achieves that by maintaining log probability. Of course, over here I didn't use the log, but I used the absolute probabilities here, but the path is very small and it's very short, and we don't have any problems with underflow. So maintaining the log probability of each branch. So we have here 1, 2, 3, 4 branches. 2 of them have been calculated and shown, because this is enough to make the point of each branch of each branch, and maintains capital K branches. So for capital K is equal to 2, in fact we are going to be, as we discussed, selected here, so docked and home will actually have been kept in this case. And finally, with K is equal to 2, the most likely sequence of the 2 corresponds to K is the ship sailed home. And this will actually what we produced at the translation. So that is what I mentioned earlier about the correction step to obviously, according to the Viterbi kind of algorithm, help us translate the right way the target sentences. And to close the discussion on the neural machine translation, at least in its basic form without attention, I think it's worthwhile covering the topic of metrics, because we will see them, see those metrics in front of us when we look at the implementations. And there are obviously many metrics that we can discuss. One of them is called BLUE, and stands for Bilingual Evaluation Under Study. It was invented by IBM many decades ago, 20 years ago, 2002. And obviously, it has many variants, but it is very frequently kind of quoted. That's why we selected to actually cover that. And this metric is fairly intuitive, and it has to do a lot, as many other metrics we've seen in the past, with the original metrics we've seen for classification, because at the end of the day, we have a classification task in front of us here, but in neural machine translation. So let me motivate that discussion with this discussion with an example. So BLUE involves the calculation of precision using reference sentences that came from a human translator and a human expert translation, and of course the predictor that we have built over here, so that will be called candidate sentences. Okay, so let me give you an example. Let's assume that we have the candidate sentence that it is the plane. So this is the translation. The plane flew in from, let's say, Athens. Okay, and we have 2 human experts that they received the source sentence, and they offered their 2 reference sentences. So this is the plane. The first expert translated: the plane took off from Athens. Obviously, this one does not spell good news for our predictor. And the other sentence is the plane departed from Athens. Actually, I'll take that back, what I just said about not spelling good news. Okay, so we'll see exactly how the BLUE is sort of working, and then we can make some comments. So in summary, what BLEU is, so to make the definition, so BLEU measures similarity using the so-called n-gram overlaps. So let's see exactly what an n-gram is and look at this sort of a bit more. So let's look at the bigrams as an example. Let's form all the bigrams that are associated with the sort of a candidate sentence. All right, so bigrams from the candidate sentence. So we have bigrams, stands for bi, stands for two, and we have gram stands for the corresponding, gram stands for the Greek word gramma, which means letter, but in this case they are words. Okay, so we have the first bigram, the plane. The other bigram is plane flew. The other one is, let's say, flew in. The other one is, I forgot to mention that bigrams are consecutive, so that's why I don't have all the permutations here. Flew in from, and from Athens. So now that we have formed, if you like, these bigrams, we will be forming the usual kind of a precision metric, which, if you recall from the kind of binary classification radar video, we know it is the true positive divided by true positive plus false positives. Okay, so in order for us to understand kind of what BLEU represents, we are going to need to translate the something to correspond to true positives from here, and something else to correspond to false positive events. We have to count events to create this kind of precision metric. So the true positives are going to correspond to the following. There are in general n-grams in the candidate sentences. We only have here one in candidate that are also in reference sentences. How many references we have. And the false positive over here is going to be n-grams, probably you have guessed it, in candidate that are not in reference. Okay, so that is the false positive. So let's look at the bigrams of the candidate. So evidently the plane corresponds to a true positive. The plane corresponds to true positive because it's part of a reference. Plane flew. Well, no reference has it, so that's a false positive. Flew in. That is also false positive. In from, also false positive. And from Athens, that is definitely a true positive. So in terms of precision over here, this kind of metric, we have two true positives divided by two true positives plus 3, and therefore the precision is 2/5. So the actual BLEU metric is more complicated than this kind of discussion we just had, because we need to calculate precisions for many types of n-grams, so not only the bigrams we see here, but trigrams and so on, or unigrams. And we need to calculate the geometric mean of those, and also account for the so-called brevity penalty that is actually called here beta. And for that kind of reason, this description is going to be fairly involved as to what exactly is being calculated here. And in the references in your notes, we are pointing to the so-called evaluate library from Hugging Face, also as well also offering some other Python code to from NLTK to actually see exactly how the sort of precision metrics are being calculated and what will be the corresponding blue metric.